Welcome to the Deep Dive, your shortcut to getting well-informed on complex topics fast. Today, we're plunging into a world of unseen chemical activity.
Mm.
It underpins so much, really. Think about environmental challenges or even just, life processes within us. Yeah, like the water crisis in Flint, Michigan. That wasn't just about pipes, was it? It was deep down a chemical battle. The wrong conditions led to corrosion, releasing dangerous lead. Or, closer to home, think about your own body. Right this second, there are thousands, literally thousands, of chemical reactions happening in, well, the watery environment of your cells. They're keeping you going. So this deep dive, it's your guide to understanding these fundamental processes. We'll focus on the three main classes of reactions in aqueous solutions and water's absolutely critical role.
Exactly. And our mission here, for you listening, is really to equip you with a clear, engaging grasp of these key chemical ideas, the laws behind them, how they're used in practice. We want to help you visualize this chemistry, translate those textbook diagrams, those equations, into insights that actually click, give you those moments. Think of it as your audio guide to how matter changes at the molecular level.
Absolutely. So what's on the agenda? We'll kick things off by looking at water itself, its unique polar nature, how different things behave when dissolved in it. We'll talk about how chemists measure the concentration, the amount of stuff in a solution, specifically molarity. Then we'll really get into the main event, the three big types of aqueous reactions. That's precipitation, acid-base, and oxidation-reduction, or redox, as you'll often hear it called. And we'll wrap up by looking at something cool, the idea that reactions aren't always a one-way street. We'll touch on reversibility. Okay, let's dive in. First topic, solution concentration and water's role as a solvent. Water isn't just like a passive backdrop, is it? It's actually a major player.
Oh, definitely not passive. It's a real chemical powerhouse. And that power, it comes from its molecular structure. See, a water molecule isn't symmetrical. The oxygen atom, it pulls on the electrons it shares with the hydrogen atoms much more strongly. It's more electronegative. This creates what we call polar bonds. So the oxygen end gets a slight negative charge, and the hydrogen ends get slight positive charges. Like a tiny magnet, but, lopsided.
Right, like a tiny battery with different poles. And its shape is bent too, like a V.
Exactly. It's bent, not linear. So that polarity of the bonds, combined with the bent shape, makes the whole molecule polar. It has distinct positive and negative ends.
Okay, so this polar, slightly charged nature,
Huh?
how does that let it dissolve something like table salt, NaCl? That seems like a strong structure to break apart.
That's where the action happens.
Hmm.
In salt crystals, you've got positive sodium ions and negative chloride ions held tightly together. But when water molecules arrive, those polar ends get involved. The negative oxygen ends of water are attracted to the positive sodium ions, and the positive hydrogen ends are attracted to the negative chloride ions. They basically swarm the ions, pulling them away from the crystal lattice. They surround them, solvate them. The water's attraction overcomes the ions' attraction to each other.
Solvate it. So they're completely surrounded by water
Oh,
molecules.
pretty much, yeah. They're enveloped. And now these ions are free to move around in the solution.
Ah, okay. So if these ions are moving charges, does that change the solution's properties compared to, say, dissolving sugar, which isn't ionic?
Big difference. Because you have mobile charged particles, the ions, the solution, can now conduct electricity. We call substances like salt electrolytes. Since salt dissolves completely into ions, it's a strong electrolyte. It conducts electricity well. Sugar, on the other hand, dissolves, but the molecules stay intact. No free ions, so it's non-electrolyte. No electrical conductivity. And then you have weak electrolytes, like acetic acid, that's the acid in vinegar. They only break apart or dissociate a little bit, so they conduct only a small current. It really hinges on whether you get those free-moving charges.
Right, it's all about those mobile ions.
And what's really neat is how we quantify this. Knowing the concentration is super important. The most common way chemists express this is molarity, symbol M. It's defined simply as moles of solute per liter of solution.
Moles per liter. Okay, so that gives you a direct count, essentially, of how many solute particles are in a given volume.
Exactly. It's
Yeah.
incredibly practical. If you know the molarity, you can easily figure out how many moles of your substance are in any volume you measure out, or what volume you need to get a certain number of moles.
Super useful in the lab, I imagine, or even in medicine, making IV solution.
Absolutely. And it dictates how we prepare solutions accurately, too. If you're making one from a solid, you'd carefully weigh out the right mass of your solute. Then you transfer it to a special piece of glassware, a volumetric flask, which has a very precise volume mark. You dissolve the solid in some solvent, and then you very carefully add more solvent right up to that mark.
Mhm.
You're creating a specific final volume of solution.
Got it. Not just adding a set volume of water.
Right, and dilution is similar. Think about making juice from concentrate. You add water, increasing the volume. But the amount of the actual juice concentrate the solute stays the same, doesn't it? So the moles of solute before dilution equal the moles after. That gives us a simple equation. Molarity concentrated times volume concentrated equals molarity dilute times volume dilute. Or M1V1 equals M2V2. Very handy.
Makes sense. Okay, let's shift gears to the first major reaction type, precipitation reactions. This is where you mix two solutions, both containing dissolved ionic compounds, and suddenly a solid appears.
That's the gist. An insoluble product forms, we call it a precipitate, and it literally falls out of the solution. It's often quite dramatic to see. Think about coral reefs forming in the ocean. That's essentially a massive, slow precipitation process building calcium carbonate structures.
Wow, so why does this happen? Why do some ions suddenly decide to clump together instead of staying dissolved?
It comes down to a competition of attractions. For certain ion combinations, their attraction to each other is just stronger than their attraction to the surrounding polar water molecules. So instead of staying happily solvated, they find each other, bond tightly, and form a neutral solid that water can't easily keep apart.
Okay, and chemists have ways to show what's actually changing, right? You mentioned different kinds of equations.
Yes, three main ways. First is the molecular equation. Shows all compounds as if they were intact molecules, even the soluble ionic ones. It's maybe the least realistic picture of what's actually in the beaker. Then there's the total ionic equation. This one's better. It shows all the soluble ionic compounds broken up into their actual solvated ions. Everything is truly floating around. But when you look at that total ionic equation, you often see some ions are exactly the same on both the reactant and product sides. They didn't change, they just watched.
Ah, the spectators.
Exactly, spectator ions. They're important for charge balance, but they aren't part of the chemical transformation itself. So the third and most useful equation is the net ionic equation. Here we remove those spectator ions. What's left shows only the species that actually react to form the precipitate. It gets right to the heart of the chemical change. That's the real story.
That seems much clearer. But how do you know if a precipitate will even form when you mix two solutions? Is it just guesswork?
Not at all. Chemists use a set of empirical observations called solubility rules. They're like a cheat sheet based on experiments. For example, rules tell us that compounds containing group 1A ions like sodium, potassium are generally soluble. Same for compounds with nitrate ions. Other rules tell us things like most salts containing carbonate or phosphate or chromate ions tend to be insoluble unless they're paired with those group 1A ions or ammonium. So by checking the potential products against these rules, you can predict pretty reliably if something solid is likely to form.
Got it. And these are sometimes called metathesis reactions.
Yeah, or double displacement. Metathesis comes from Greek meaning to transpose. It's like the ions swap partners. If AB reacts with CD, you get AD and CB. Sometimes one of those new pairs is insoluble.
Okay, moving on to our second big category, acid-base reactions, often called neutralization. What's the core event here?
The key event, especially in strong acid, strong base reactions, is the formation of water. It fundamentally involves the transfer of a proton, an H+ ion. We see this everywhere. Think stomach acid, hydrochloric acid helping digest food, or taking an antacid, which is a base, to neutralize excess stomach acid.
So, defining terms, what makes something an acid or a base in this context?
Good question. The common definition, the Arrhenius definition, says an acid is a substance that produces hydrogen ions, H plus Rho, when dissolved in water. Though technically that H plus is just a proton and immediately latches onto a water molecule to form the hydronium ion, H3O plus plus Rho. So H plus AQ and H3O plus AQ are often used interchangeably. A base, then, is a substance that produces hydroxide ions, OH, when dissolved in water. Sodium hydroxide, NaOH, is a classic example.
And just like with electrolytes, acids and bases can be strong or weak.
Exactly the same principle applies. Strong acids and strong bases dissociate completely in water. Every molecule breaks apart into ions. They're strong electrolytes. Hydrochloric acid, HCl, nitric acid, HNO3, sodium hydroxide, NaOH, potassium hydroxide, KOH. Those are common strong ones. Weak acids and weak bases only dissociate partially. Maybe only 1% or less of the molecules break into ions at any given time. So they're weak electrolytes. Acetic acid in vinegar is a typical weak acid. Ammonia, NH3, is a common weak base. This difference hugely impacts their reactivity and pH.
So if a strong acid reacts with a strong base, what does that look like at the ionic level?
It simplifies beautifully. Take HCl and NaOH. The total ionic equation shows H plus, Cl, Na plus, and NOH ions. But Na plus and Cl are spectators. They just stay dissolved. The net ionic equation becomes simply H plus Aq plus OH Aq AH2O. It's a direct combination to form water, the essence of neutralization.
What about a weak acid, like acetic acid, reacting with a strong base like NaOH?
Slightly different. Because acetic acid, He2H3O2, is weak, we write it as an intact molecule in the ionic equations, since most of it is intact. So the net ionic equation shows the acetic acid molecule directly donating its proton to the hydroxide ion, He2H3O2Aq plus OHAQ plus H2OL. You see the proton transfer explicitly from the weak acid.
Interesting. And sometimes these reactions make gas, like the classic baking soda and vinegar volcano.
Absolutely. That fizzing is CO2 gas. When acids react with carbonate ions, CO32 like in baking soda, sodium bicarbonate or sulfide ions, S2, you often get gas formation. With carbonates, the acid protonates the carbonate, forming carbonic acid, H2CO3, which is unstable and immediately decomposes into water and CO2 gas. That's your bubbling. The carbonate acts as the base.
And just like with precipitation, we can measure these reactions precisely, using titration again.
Yes. Acid-base titrations are a cornerstone of analytical chemistry. You use a solution of known concentration, a standard solution, maybe a base, to find the unknown concentration of another solution, say an acid. You add the known solution slowly from a burette, a calibrated glass tube, into the unknown solution. You need a way to know when you've added exactly enough base to neutralize all the acid. That point is called the equivalence point. We use an indicator, a substance that changes color at or very near the equivalence point's pH. Phenolphthalein is common. It goes from colorless in acid to pink in base. That color change signals the end point of the titration, which tells us we're done. Right, that visual cue. Okay, on to our third major class, and you said this is where it gets really interesting. Oxidation-reduction, or redox reactions.
I think so. Redox reactions are all about the movement of electrons between reactants. This electron transfer, or sometimes just a shift in electron sharing, is fundamental. It powers so much around us and in us. Batteries, redox, rusting, redox, combustion like burning fuel, redox, how your cells generate energy from food, also redox. So electron movement is the key. Does it have to be a complete transfer, like forming ions?
Not always. It can be a full transfer, like when magnesium metal reacts with oxygen gas to form magnesium oxide, MgO. Magnesium atoms literally lose electrons, becoming Mg2 plus ions, and oxygen atoms gain electrons, becoming O2 ions. That's a clear transfer. But it can also be a shift in electron density. When hydrogen gas reacts with chlorine gas to form hydrogen chloride, HCl, they form a covalent bond. But chlorine is more electronegative. It pulls the shared electrons closer to itself. So even though it's not a full transfer, electrons have effectively shifted away from hydrogen and towards chlorine. That still counts as redox.
Okay, so there's specific language for this electron movement, right? Oxidation and reduction.
Exactly. Oxidation is defined as the loss of electrons. Reduction is defined as the gain of electrons. A helpful mnemonic is Leo the lion says GER. Loss of electrons is oxidation. Gain of electrons is reduction. And they always happen together. If something loses oxidation, is oxidized, something else must gain them, be reduced. The substance that causes oxidation by taking electrons is called the oxidizing agent. It's the one that gets reduced. The substance that causes reduction by giving electrons is the reducing agent. It's the one that gets oxidized. Two sides of the same coin.
Ilio says GER. Got it. But how do you track this, especially if it's just an electron shift and not a full transfer?
That's where oxidation numbers, sometimes called oxidation states, come in. They're a kind of bookkeeping tool for electrons. We assign an oxidation number to each atom in a compound based on a set of rules. It represents the charge the atom would have if the electrons in its bonds were completely transferred to the more electronegative atom. For example, an atom in its pure elemental form always has an oxidation number of 0. For a simple ion like Nam plus A, the oxidation number is just its charge plus 1. Oxygen in most compounds is -2. Hydrogen is usually plus 1. There are rules to figure it out for everything.
Okay, so you assign these numbers. How does that tell you if it's redox?
You compare the oxidation numbers of atoms in the reactants to their numbers in the products. If an atom's oxidation number increases during the reaction, it means it lost electrons, became more positive or less negative, so it was oxidized. The substance containing that atom is the reducing agent. If an atom's oxidation number decreases, it means it gained electrons, became less positive or more negative, so it's reduced. The substance containing that atom is the oxidizing agent. If the oxidation numbers change for any elements in a reaction, it is a redox reaction. If they all stay the same, it's not redox.
So it's a clear check. And
Yeah.
can you do titrations with redox reactions too?
Absolutely. Redox titrations work on the same principle as acid-based titrations. You use a known concentration of an oxidizing agent to react completely with an unknown amount of a reducing agent, or vice versa. A classic example uses the permanganate ion, MnO4. It's deep purple. When it acts as an oxidizing agent in acidic solution, it gets reduced to Mn2 plus Wam, which is nearly colorless.
Right.
So as you add the permanganate solution, the purple color keeps disappearing as it reacts. The instant all the reducing agent is used up, the very next drop of permanganate makes the whole solution turn a faint pink or purple because there's nothing left to react with it. The permanganate acts as its own indicator. That is called self-indicating. Okay, briefly, are there common patterns or types of redox reactions involving elements? Yeah, we can categorize them. Combination reactions, where elements combine to form a compound, are often redox, like a metal reacting with a nonmetal to form an ionic salt. Here, Gk plus Cl2 next to Cl. The metal loses electrons, oxidized, the nonmetal gains them reduced. Decomposition reactions, where a compound breaks down into elements or simpler compounds, can also be redox, often driven by heat or electricity, like heating mercury oxide to get mercury metal and oxygen gas. Then there are displacement reactions, which we touched on. One element displaces another from a compound.
Right, the activity series for metals.
Exactly. That activity series ranks metals based on how easily they lose electrons, how easily they are oxidized. A metal higher on the list can displace or reduce the ions of any metal below it from solution. So zinc is higher than copper, meaning zinc metal will reduce C2 plus ions, forming zinc ions and solid copper. Lithium is so reactive it can even displace hydrogen from water. There's a similar activity series for halogens, too. Fluorine's the most reactive. It can oxidize chloride, bromide, and iodide ions. Chlorine can oxidize bromide and iodide, and so on down the group.
And what about combustion? Burning things.
Always redox. Combustion is rapid reaction with oxygen, producing heat and light. Oxygen O2 is almost always the oxidizing agent. Whether it's burning natural gas, wood, or even the burning of glucose in our cells for energy, cellular respiration, it involves the transfer of electrons to oxygen.
Okay, we've covered a lot of ground on reactions, but there's one more key idea: reversibility. We tend to think reactions just go, right, reactants become products, end of story.
That's often how we first learn it, but it's not the whole picture. Many, maybe most chemical reactions are actually reversible. The products can react to reform the original reactants. This leads to a state called dynamic equilibrium.
Dynamic equilibrium sounds like a contradiction.
It does a bit. But dynamic means it's active. Equilibrium means there's a balance. It's the state where the rate of the forward reaction, reactants, products, becomes exactly equal to the rate of the reverse reaction, products, reactants. So on a large scale, the amounts of reactants and products seem constant. It looks like nothing is happening. But at the molecular level, both reactions are still occurring constantly, just at equal speeds. There's no net change, but plenty of ongoing activity. Think of people walking onto and off an escalator at the same rate the number of people on the escalator stays constant, but it's not the same individuals.
Ah, okay. So the reaction hasn't stopped, it's just balanced. Does this connect back to things like weak acids?
Perfectly. Why are weak acids weak? Because their dissociation into ions, forward reaction, quickly reaches equilibrium with the reassociation of those ions back into the acid molecule, reverse reaction. Only a small fraction is dissociated at any moment because the reverse reaction is significant. That is dynamic equilibrium. Even reactions we consider complete, like precipitation or strong acid-strong base neutralization, technically reach equilibrium. It's just that the equilibrium lies very, very far towards the product side. The reverse reaction is extremely slow or unfavorable, so for all practical purposes, it looks like it went to completion.
So it's really about the position of that equilibrium.
Exactly. How far does the reaction proceed before the forward and reverse rates become equal? That's a huge question in chemistry.
It definitely changes how you view these processes, not just as start-to-finish events, but as ongoing balances.
Which leads to a thought for you to consider. Given this constant dance, this back and forth of electrons and protons we've talked about, think about something in your daily life that seems completely stable, unchanging. Could it actually be a site of intense, balanced chemical activity? A hidden dynamic equilibrium happening right under your nose?
That's a fascinating thought to leave with. We've really covered some essential ground today, from water's amazing polarity to how we measure solutions through the big three reaction types: precipitation, acid-base, and redox. And finishing with this crucial idea of dynamic equilibrium, hopefully you feel like you have a much clearer picture now of the chemistry happening all around and inside you. We really encourage you, keep looking, keep asking questions, keep diving deep into how the world works.
Thank you for joining us on this deep dive.
From the Deep Dive team, we're always here to help you get well-informed, fast.